Hey, so in this lesson, we're going to be talking about probability. We're going to talk about it's really just going to be like an introduction, nothing in deep. 'Cause I think it's pretty simple. So just to kind of introduce it to you. So we're going to talk about what is probability. We're going to talk about experiments, outcomes, and events. We're going to talk about some set operations as it relates to these events. And then I'm going to show you two of the common, most mathematical, like probability discussions around rolling a die or flipping a coin. And then, of course, common mistakes and key takeaways. What is probability? Essentially, at its very basic level, probability is just the likely of something to happen. I know a lot of times when people think probability, you think, oh, chance and lottery and winning a prize and all of that. But just think of it at its very base foundation is how likely is something to happen. And then basically what it does, it puts a number on it. 50% chance, 30% chance, 20% chance. It's not that it guarantees that there will be like a positive outcome or a negative outcome. You're just saying, what is the likelihood of something happening? Weather Channel, for example, what is the 30% chance of rain, 20% chance of rain? What is the likelihood, high probability, low probability chance of something happening? That's essentially what probability is at its lowest level. Now, when we explain it in math, we tend to use things like rolling a dice or flipping a coin, just so that you can kind of mathematically see how it works. But you deal with probability each and every day in real life. So this is a real life thing, and it's not just about gaming and chance and winning prizes. These are just things that you do automatically, because remember, at the end of the day, math is just simply critical thinking. So in the real world, like I said, weather forecasting, car insurance pricing, certain individuals are priced higher than other individuals. Why? Because of the likelihood of getting into a car accident, the likelihood of getting in a car accident depending on where you live. Medical treatments, a lot of medical treatments are here today and work because they've gone through experiments, they've gone through trials to figure out what's the probability, what's the greatest chance of survival with taking this particular medication or going through this particular medical scenario. Your social media posts, try to keep it fun. What are the chances of you going viral? What makes a video go viral? There's actually data information out there that you can put a number on the high probability of you going viral versus the low probability of you going viral. I did rock, paper, scissors. If you remember that as a kid, you play rock, paper, scissors. What is the chance of you winning? How high likely is that chance? And then my all-time favorite, which I kind of laugh at, is at the grocery line. If I switch from this line, this slow line, to this line over here, what is the chance that my line's going to move faster? At the end of all of that, at its very foundational level, again, it is probability. Okay, so I don't want you to think it's just a math term. It is essentially probability. Before we actually jump into percentages, let me paint the picture of what makes up probability. So you normally what you call is this random experiment. So let me read this to you. So mathematically, it says a random experiment has outcomes that we cannot predict, but has a regular distribution in a large number of repetitions. What does that even mean, right? So essentially what that means is you can determine the outcome of a scenario if you have repeated experiments, meaning however it happens over the long run, it gives you a greater chance of seeing a high probability or a low probability. So essentially you're just looking at patterns to determine what's predictable and what's not predictable. So when you're talking about a random experiment, that could be anything. Like I said, don't think of just a random experiment as like a medical experiment or you flipping a coin or you rolling a die, but think of it as like with the car insurance. If you think of all the people that they insure, that can be considered an experiment. And you say, okay, what's the highest probability that this individual would end up in a car accident or would not end up in a car accident? Okay, so an experiment is just looking at patterns over the long haul to determine what the outcomes are. In a random experiment, there's a thing, when you repeat it, it's called a trial. So every time you repeat this particular experiment, you say, okay, I'm doing this trial. And when I do this particular trial, I have an outcome. And the set of all possible outcomes is called a sample space. That's just a set of all the outcomes that have happened. Now, what I typically use in this is Skittles, because Who doesn't like Skittles? But anyway, so if I tell you that I wanted you to take this box of Skittles and I wanted you to pick 5 Skittles from this box. So this is my experiment, my random experiment. You're going to select 5 Skittles. You're going to pull out 1 Skittle at a time. Every time you pull out a Skittle, that's called a trial. That is a particular trial. And then when you look at what you pull out, did you pull out a red, green, orange, purple, yellow? If you pull one of those out, whatever the outcome is, or whatever the outcome of that trial is, you say that's the outcome. So whatever you pull out, if you pull out a red, that is the outcome of that particular trial. So each time you pull, you're going to have an outcome. So since I've asked you to pull a total of 5 Skittles, you're going to have 5 possible outcomes out of this entire box. So again, red, green, yellow, purple, orange, whatever you pull out. Whenever you do all 5 Skittles and you pull them out of the box, whatever you end up with, that builds your sample space. That is your sample that you can use for other things. So like when they're doing like medical experience or medical trials. Now, I don't want you to confuse medical trials with this particular word trial, but basically what they do is you notice it starts off as a large group of people. And then as outcomes start to happen, they start to get to this small group and they say, hey, we noticed with this small sample space, these things were good, these things were good, these things were good, or these things were bad. So you start big with a box of Skittles, and then as you perform your trial, you end up with a set of outcomes, and that set of outcomes is called your sample space. So if you look at this particular example on the screen, notice you could get all reds, right? You could pull 5 reds. You could do red, green, red, green, red. You could, I know the yellow is hard to sing, but you could do yellow, 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 red, and orange. There's so many different possibilities out of all of these trials. So that's just what I want you to understand, is that you have a random experiment. So when you're talking about setting this up, you have a random experiment, whatever that experiment is. Each time you do a certain activity, that is called a trial. And then every trial, you produce a outcome. Okay, no matter good, bad, it's not about good or bad. It's what is the outcome of me performing that said activity. So let's look at a mathematical example with flipping a coin. So we have a random experiment. I want you to flip a coin 1 time. Remember, your random experiment is whatever the thing is that you're asking the individual to do. The trial is flipping the coin. And then the outcome, we know when you flip a coin, you're either going to get heads or tails. So if you flip a coin twice, you have your first flip, that's your first trial. You can either get heads or tails, correct? So if you look on the screen, I have heads and I have tails. Well, if you flip again, if you got heads first and you flip the coin again, you can get heads or tails again. So you notice that when I flip the coin the first time, I have 2 outcomes, head or tails. If I flip the coin again, I'm going to have 2 outcomes, heads or tails. See, it just keeps repeating with each trial. So in this particular example, each flip is considered a trial. So again, on my first flip, I could get heads or tails. If I get tails on my first flip and I flip the coin again, I could get heads and tails again. So you say, okay, well, what is my sample space? What is the group of possible outcomes that I can get when I'm flipping a coin twice? Well, when you think about it, you can get heads and then heads on the second flip, or you can get heads on the first flip, tails on the second flip, or tails on the first flip, heads on the second flip, or you can get tails and tails. So in this particular experiment, even though I only have 2 trials, which each flip of the coin is a trial, I have 4 possible outcomes: heads, 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 tails, tails, heads, and tails, tails. Those are the 4 possible outcomes. So you see, it's very simple. And like I said, I'm using these very basic math examples just so you can wrap your head around the concept. So our sample space is 2 heads, a heads and a tails and a heads, or you can get 2 tails. Each outcome is called an event. So when you're talking about the particular outcome, a lot of times they'll say the outcome of getting whatever, the outcome. So if I said the event of getting one head and one tails would look like this. And notice on the image, I'm using the squiggly lines. These represents what we call sets in mathematics. You're just set, it's like a group of if you want, for this example, it would be a group of outcomes that we're putting together. But if I'm talking about a specific event out of all the possible outcomes, then you call it an event, and you also put them in squiggly lines. So if I said the event of getting one head and one tail, it would just be, I used E for event, and then you have heads, tails, or tails, heads. If I said how many events would getting two heads, well, there's only one event, because you would have to flip a heads on the first, flip a heads on the second, and then you would have heads. So, and each outcome is called an event. You're rolling a fair die. Now I have to say a fair die because in the real world you do have, what do you call it, bogus dies. I forgot what they call it, where it always lands on 6. Watch out for people like that. But I have to say a fair die so that you know, okay, when you roll this die, just one, you're going to end up with a 1, 2, 3, 4, 5, or 6. That is my sample space. Those are the only numbers that I can end up with. Now, that means there are 6 total outcomes. You can roll a 1, you can roll a 2, 3, 4, 5, or 6. There are 6 total outcomes when you're talking about rolling a die. Now, if I start talking about events, so if I'm looking at all the 6 outcomes, what is the event that the die that I roll shows a 5? This is how you would write it. H, if I say H is the event that die shows a 5, you would put the 5 in the squiggly. That's your set. That's the event. You're just naming it. So again, we're just going through the foundation so you can wrap your mind around it. If I say the event J is the die shows a number less than 10, well, that's going to be 1, 2, 3, 4, 5, and 6. And notice that event J is exactly the same as the sample space at the top of the slide. So that means it's for certain you're going to roll a number less than 10. If I said you rolled a, let's see. Yeah, if I say like the event K is if you roll a 9, well, there's no way you can roll a 9. And notice this has this little null. This is an impossible event. And we're looking at K at the bottom of the screen. That is not the number 0. That means an empty event. This is an impossible event. It just means it can't happen. So don't get confused with the null and the 0 or a blank, and a squiggly lines with it. I should have written that on there. This means a null event, or it means an empty event. It's an impossible event, and it cannot happen. Okay, so that's what that means. Okay, let's look at some more examples. A die event E where the number shows less than 3. Well, that event would have 2 outcomes, 1 and 2. Because you can roll a 1 or you can roll a 2. If I say the die shows an even number, well, that's the event of rolling 2, 4, or 6. Or if I said a die shows an odd number here at the bottom, that means it would be 1, 3, or 5. So there's so many different events that you can come out of looking at a particular sample space. So you're limited to the sample space, but just know you can come up with different events. And then remember, an event can be for certain, that you know for certain it's going to happen, like rolling a number less than 10. Well, that's going to happen because you have 6 choices. And then you have what you call impossible events, which cannot happen because you're not going to roll a 9. So because events are sets, remember we're writing them in these little squiggly lines. In math, that represents a set. So because events are sets, you can actually use set operations. So hopefully this is a refresher. I did do a video on set operations, and I can provide the link to that so that you can refresh your memory on that. But this first, if you look at this first, it says let E and F be events for a sample space S. Then E, that upside down U, that's an intersection. That means intersection. That means if the item is in E and it's also an event F, and you can put them together, then you would say the intersection of set E and F. They would go together. And I'll show you some examples. This next line, the EUF, that U represents union. That means or. So if the event E can happen, or event F can happen, or if they both can happen, then you can find the union of those events. And then this the next line, the little tilde, I call it a tilde, but the little apostrophe next to the E, that's called the complement of E. So if E is rolling, a 1 through 6, then not E would be not rolling 1 through 6. So it's almost like the opposite of whatever the event is. And then if two events, when you do the intersection of two events, this last line here, and it's equal to the null set or the empty set, then you would say these two events are disjoint. That just means they don't have anything in common. So again, I'll link my my video on set so that you kind of have that, so that you remember, you can refresh your memory on what that is. So the upside down U that looks like a hut, that represents intersection, meaning you intersect the two sets if you can. The U is union, that means either or. You can union the two sets. And then, of course, the E with the apostrophe, that just means the complement or the opposite of said event. So let's do some examples. Let's go back to the die because it's just really easy. So if I have event E, which is rolling a 1 or a 2, event F, which is rolling a 5, event G, which is rolling an even number, and event H, which is rolling an odd number. If I wanted to find the intersection of set E and F, it does not exist. Why? Because set E is rolling the event that you roll a 1 or a 2, and set F is the event that you roll a 5. They don't have anything in common. You either roll a 1 or a 2 or you roll a 5. So that's why this is equal to the null set. These two sets would be disjoint because they don't have anything in common. See? Very simple. Set F is rolling a 5. Event F, is rolling a 5, and event G is rolling an even number. Well, 5 is odd, so they don't have anything in common. So the intersection of event F and event G, or if I want to say set F and set G, would also be null, the null set, and these would be disjoint sets. E and H. E intersect. Intersect means and. So it would have to exist in both these events. E is the event that I roll a 1 and a 2, or 1 or a 2, H is the event that I roll a 1, 3, and 5. Well, the intersection of those two, what elements do they have in common, is rolling a 1. That's why that's the set 1. Easy? Okay, E union F. So either I roll a 1 or a 2, or I roll a 5. When I union those events together, I get 1, 2, and 5. So see, union means one or the other or both, and intersection means it has to happen in both of them in order for them to exist in the set. Again, leave any questions that you have. I'm trying to make it very plain here. F union G. F is rolling the event that you roll a 5. G is the event that you roll an even number. Since it's the union, one or the other or both, then that becomes the set 2, 4, 5, and 6. Because I can do one or the other. I can roll a 5 or I can roll an even number. And then G or H. That ends up being matches the sample space, right? G is rolling an even number, or you roll an odd number, which is event H. And so when I union those two events, I get 1 through 6, which matches the sample space, which again, that means that this event is for certain because it matches. It's going to happen. Now that you have a foundation set, we can talk about probability. So now you either have probability on equally likely outcomes, or you have probability on things that aren't equally likely. And then I'm going to show you the difference between the two. When you roll a die, rolling a number between 1 and 6, it's always 1/6. That's your probability, because rolling a 1 is 1 out of 6. Rolling a 2, you have 1 out of 6 chances. Rolling a 3, you have 1 out of 6 chances. If you roll one time, you have a chance of getting 1/6 for whatever number that you roll. Likewise, when you're flipping a coin, you're either going to get heads or you're going to get tails. So the probability of you getting a heads is 1 out of 2 or half. The probability of you getting a tails is also 1 out of 2 or half. So that's where probability comes into play. It's what you're trying to get, dividing by however many chances you can have said outcome. So if you have a sample space, now we're getting into the math definition. If you have a sample space that have equal likely outcomes, meaning each outcome is likely, has the same chance of happening. Each outcome has the same chance of happening. Rolling a number on a die, it's 1 out of 6. Flipping a coin and getting heads or tails, it's 1 out of 2. Each outcome has the same chance of happening. And then it says an event E is a subset of S. A subset just means a smaller set. So if my sample space is 1 through 6, and remember we were going through all those events, they were smaller, it just means a subset. The way you find the probability that event E's occur is this formula here at the bottom. You take the number of items in that event, what you're looking for, and you divide it by the number of items in the sample space. That's why when you roll a die, you have, if I say, what's the probability of me rolling a 3? Well, that's going to be 1 out of 6. Why? Because there's 1 3 in that event, and I have 6 outcomes in the sample space. Single flip of a coin, same thing, 1 out of 2. Why? Because if I say what's the probability of me getting a heads, that's 1. I have 1 chance to get a heads out of 2 outcomes. Because every time you flip a coin, you're either going to get heads or gets tails. And then another thing that you want to remember about probabilities, your probability is going to be between 0 and 1. So it can't be greater than 1 and less than 0. If that happens, then you're doing something wrong. And when you add up all of the probabilities, if you look at all of the outcomes in the sample space, and if they all have an equal chance of happening, and you add all of them up, they should add up to 1. Let me show you what I'm talking about. So when your sample space for rolling a die is, you either have 6 choices, right? If I roll a 1, that's 1/6. Roll a 2, that's another 1/6. Roll a 3, 4, 5. They all have the same chance of happening, right? They all can 1 out of 6 chances of happening. Well, if I go and I add all of those up, rolling a 1, rolling a 2, rolling a 3, 4, 5, or 6. If I add all those up, and when you add fractions, they have the same denominator, that's 6 out of 6. And we know that 6 out of 6 is 1. So your entire sample space, this only works if each outcome has the same probability, the same chance of happening. Same thing with flipping a coin. A half plus a half is a whole. Six outcomes, you add up all 1/6. 6 out of 6 equals 1. Make sense? Good. Okay, so let's look at some examples. I'm still going to stick with the dice because you get more examples. So if we know that each roll is 1/6 of a chance of getting a 1, 2, 3, 4, 5, or 6, it doesn't matter. Let's go back and look at those events that we came up with. So what's the probability of rolling a 1 or a 2? Well, I'm looking at this first one here in green. That's 2 out of 6. Why? Because I can roll a 1 or a 2. That's 2 items in that event, and I have 6 chances of doing it. I have 6 outcomes. So that's 2 out of 6. And when you simplify that, that's 1 out of 3. So if they want, depending on what your assignment asks for, if they want just the solid probability so you can see how they all add up to 6, that's fine. But if they ask you to simplify it, you would just simplify this to 1/3. Now let's look at the purple event. F is the event that I roll a 5. Well, there's only one way I can roll a 5 out of 6 opportunities, out of 6 outcomes, 1 out of 6. Rolling an even number, there's 3 even numbers, 2, 4, and 6. So that's 3 out of 6 outcomes are going to be even. That's 1/2 when you simplify that. And then the same thing for odd numbers. I have 3, 1, 3, and 5. If I divide that by 6 chances, I still have. So that means I have a 50% chance of rolling an even number, and I have a 50% chance of rolling an odd number. See how that works? What happens when it's not equally likely outcomes, not flipping a coin, not rolling a die, not those very generic? What you do is you look at the history of it. So if you look at these examples here, I say that we rely on the frequency of what we know over the long run. How do they know that around this time of year that it's going to get cold? Because historically in Texas, it has gotten cold around this time of year. How do they know the percentages that it's going to rain or not rain? Because they're looking at the data and so based on the information that we see, there's a high probability of it raining. In education, a lot of colleges know when it's around May time, you tend to get higher grades. Why? It could be because students are ready to graduate. Students know the summer is coming. Why during the fall semester? Why are grades looking a certain way? They look at the data over a long period of time, and then say, well, historically, this is how it has normally happened. And then you come up with a probability based off of that. Teenagers and car insurance. Why do we know that teenage boys' car insurance is much higher than teenage girls' car insurance? Well, over a historical period of time, they've noticed that maybe teenage boys tend to be more reckless. They drive faster. They're not paying attention. They're less mature. They're on their phones. Maybe the numbers have changed now because everybody's on their phones. So that you look at the historical data to kind of come up with, okay, what has happened over the period of time? And then your household. I just did this as a funny example. Beets. When's the last time you bought beets for a beet salad? It's probably a less likely probability, I know, in my household that anybody's going to eat a beet salad. So am I going to go spend my money on beets? Probably not, because it's just probably going to be me eating them. So that's what I'm saying. When you think of real world, remember, all math is just critical thinking. How do you use this in the real world? You use it all the time. When you're shopping for insurance, when you're shopping for a home, when you're buying groceries for your household, it's either going to be Diet Coke or Coke. Why aren't you buying Diet Coke? Because nobody in my house drinks Diet Coke. How do you know? Because I physically see them jokers not drinking Diet Coke. So my chances is telling me it's a higher probability that they're going to drink regular Coke. You see how that works? It's all about the critical thinking. So when you don't have flipping a coin, when you don't have rolling a die, you look at historically Tylenol, diabetes medications, likelihood of surviving a stroke. All of these things, they have taken the time to look historically over time. If you're a certain height, a certain weight, you're subject to these issues and these issues because they've looked at the data and they rely on that data to provide you with probabilities. Make sense? So let's look at a real world example. So this one says, getting my iPad ready. So for religious services, this one says, according to 2016, the General Social Survey, GSS, which participants were asked how often they attend religious services. The following data was collected from 2,867 people. And I put the source up there. If you go to the website, they have done tons of surveys. But it gathered all this data to see what participants were asked and how often they attended religious services. Now you're like, well, Dr. B, where does this come into play? Well, it depends. If this were in the United States, or let's say this were in Texas, then they can say, well, you know what? In Texas, 50% of people do attend religious services. That's when you start honing in on where you're talking about. Now, I didn't get into the nitty gritty of where this is discussed, but that's where that comes from. You say, hey, in Canada, we surveyed these people. In Texas, we surveyed these people. In Dallas, we surveyed these people. In Austin, we surveyed these people. And then based on the survey, remember, a survey is not everybody. This was just 2,867 people, but you create a sample, and based on that sample space, you start making probabilities to determine how the whole population is affected. You see this a lot in the political realms. How do they know what percentage of people are going to vote Republican, Democrat, Independent? They're looking at the numbers, and then based on that sample space, they're making a generalization of the entire population. Now, again, this is just a foundation in the probability, but once we dive more into it, you'll see how we can start making inferences. So for this particular example, we're going to ask these questions. We're going to say, what's the probability that they attended 2 to 3 times a month, never or once a year, several times a year, at least once a month, or nearly every week or more frequently? So let's 2 to 3 times a month. And then remember the formula. If I can write it down, remember the probability of E. Remember, that's the number of that divided by the number in the sample space. And we know for this particular example, there were 2,867 people, right? Okay, cool beans. So what is the probability that out of this particular survey that they attended 2 to 3 times a month? Well, let's find it in the survey. 2 to 3 times a month is right here. So 250 out of what? 250 out of 2,867. So when you put that in your calculator, you get this nice big decimal, 0. Hold on. Put it in my calculator. 0.0871999163. Now, to change a decimal to a percent, you multiply by 100. So when you multiply this by 100, you get approximately, well, you know what? Let me shorten it. 872. And then this is approximately 8.72%. So based on this survey, approximately 8.72% of participants attended a religious service 2 to 3 times a month. So they could probably say, based on this, the general population probably attends 8.2%. All right, let's look at, what was the next one? Never. I'm going to write it like this. I'm going to say never or once a year. So never or once a year. And this was the probability of 2 to 3 times a month. Never or once a year. Well, this amount attended never, and this was once a year. So to know the probability, you want to add these two together, right? So you need once a year and you need never. Okay, so then to find that probability, that's going to be 723 were never. Sorry, I want to do it, yeah, so you can see it. 723 were never, plus 385 all over 2,867. So when you add the numerator, you should get 1108 out of 2867. When you divide that, you get this really nice long decimal, 0.38646669. So far, so good. I think I'm saving, what is that, 4 decimal places. So 0.3865. And then remember to change your decimal to a percentage, you multiply it by 100. So if I multiply this by 100, that's approximately 38.65%. So approximately 38%, or I'll say 39% of people never attended a religious service, or they attend once a year. See how that works based off of the data. The next one says the probability of several times a year. What's the probability that they attended several times a year? Well, that one's looking easy, right? Several times a year, 312. Okay, so that's going to be 312 out of 2867. And you get 0.10882455. That's approximately 0.1088, which is 10.88%. So approximately 11% of this particular population attend, several times a year. Okay. Several times a year. So you see how you use the numbers, you use what they've reported to come up with the percentage. And this one said D was the probability that it's at least once a month. Now, at least once a month means what? At least once a month is going to mean one month or 2 months or 3 months, right? That at least means more than one. Well, at least once a month, we have these people that attend once a month here. These people attend 2 to 3 times a month, nearly every week, and more than once a week. Would that account for the people that attend at least once a month? That means they attend 1 month or more, or do we go a different way? Yeah, once a month, right? Twice a month, every week, because every week, that's what, you have 4 times a month, or nearly every week, and then more than once a week. Yeah. So this would be your group of people that you put together. Now, we don't include the don't know because we don't know what they're doing, but we do include these people here, okay? So that means we got to add all those together, right? Oh, sorry. We're going to add all these together. So that's going to be 190 plus 250 plus 126. And we'll come back and check ourselves. 481 plus 210. So let's check again. Once a month was 190. Twice, 2 to 3 times a month was 250. Every week was 126. 481. Nearly every week was 126. And then more than once a week was 210. So that accounts for the people that attend at least once a month. At least once a month. Okay, so that's what we're including here, and that's out of 2,867, right? Let me scooch this up a little bit. And then when you add all of those up, you get 1,257 out of 2,867. And then you get this long decimal, so put that in the calculator, 0.438437391. I'm going to just use 4 places after the decimal, which that's approximately 43.84%. Easy, right? Yeah, pretty easy. And again, they take these numbers based off of the sample space and then they apply it to the general population. Okay, let's do this last one right here. Yeah, we got room right here. This is the probability of, they said nearly every week or more frequently. So the probability of they go nearly every week or more frequently. Every week or more frequently. Every week or more frequently. Well, they won't be in there, right? Because they never go. These people don't know. So nearly every week or more frequently. Nearly every week or more frequently. If you notice, these are less than, these are less than a week. So nearly every week, or they go every week, or they go more than once a week. You see that? So that's what we want. We want the people that go nearly every week, or they go more than that. So it's this group, okay? Because they go every week, more than once a week, every week, nearly every week. Okay, so that's going to be 126, 481, 210, right? Let's check again. Nearly every week, 126, every week, 481, and then more than once a week, 210. And remember, we excluded the don't answer because they didn't tell us where they were going. And then these people are going less than the week. So we don't want to include those. So we excluded them and we excluded those, and we're only looking at those 3. Okay? Makes sense? So that's out of 2,867 people. When you add that up, that gives you 817 out of 2,867. Let me scroll up just a little bit. That gives you this pretty decimal here, 0.284966. Sorry, 66864. Yeah, sorry, 0.284966864. So I keep 4 decimal places. Scroll that up. That's 0.28, what is that, 50? And you're like, where did I get that from? Let me show you. But see, that's a 9, so when we round up, that's got to go up, okay? That's where I got that from. And then that's approximately 28.50%. So approximately 28% of individuals surveyed go nearly every week or more frequently. Or what happens with that particular population, and then you apply it to the or this sample space, and you apply it to the population. So that's how you come up with probabilities when it's not flipping a coin or anything like that. Okay, cool. So common mistakes: not knowing the difference between outcomes and events. It's okay if you say the outcome, if you say the events, just know you're talking about what comes out of performing the experiment. The events are where you start saying you can get odd, you can get even, you can flip a coin, you get this. Those are your individual events, okay? What the outcomes. If I go back and show you the what we were looking at, every single one of these is an event. If you put everything together, that's all of the outcomes. Those are all the outcomes, but each individual thing is considered an event. Okay, so that's the difference. Don't mistake the null set for 0. That is not the number 0. It means the null set. There's nothing in common. And then you might have to refresh your memory on the union, the intersection, the null, and then the complement. Again, I'll put a link to the video that I did on that so you can get that. And then always double check behind yourself. Okay. Always double check behind yourself. Key takeaways: pay attention to the symbols so that you know if you're doing the union, the intersection, or the complement. Take your time to find the probabilities. We just did some really simple examples. And then if you start getting into where they're asking you to roll a die or flip a coin, pull out some marbles, don't be afraid to actually go get you some dice and roll it just so you can physically see what's going on. Especially with the deck of card questions, sometimes it's like, what's a spade? What's a heart? What's a red card? Lay it out so you can actually see it. And then don't forget to double check yourself and behind your work. You should be able to complete your assignment with success. Follow the steps that we covered in this video. Remember, this video was strictly an introductory, a foundation to probability. Always keep that calculator handy. Ain't no need for you to guess. And then remember, at any point during the videos, you can leave your comments and leave your questions, and I'll be sure to get back to you. All right. Talk to y'all later. Bye.